go. Good morning. Oh, right. One last time. Let's do graphs. Let's go. Good morning. Okay. So task 8, last task I'll introduce. Last one of the semester. Actually, there's one thing I wanted to check on this. For this one, we're going to use graph information, movie information to find the degrees of separation between actors. So for this one, we're going to create the degrees of separation class, which takes an array list of movies as its constructor parameter. And this is, the intended usage of this would be reading the movies from a test file, but you don't actually have to use test files for this one if you don't want to. You can manually create your array list if you don't want to mess around with files anymore. We've messed around with files for 2 tasks. If you want to create your array list manually for this one, that's fine. If you want to create your test files, that's fine too. Whatever you find easier for this one is what you can go with. And this movie information, we don't need any ratings for this one, but we do need the cast list. The method that you'll actually implement is the degrees of separation, which takes 2 cast members or 2 actors and returns their degrees of separation as an int. So degrees of separation is how many movies you would have to traverse to be able to get from one actor to another. And I always have trouble explaining exactly what this means, so I have an explanation here, or you can check out the Wikipedia article here explaining degrees of separation. But it's how many movies you would have to traverse. So for example, if an actor starred in a movie with another actor, then their degrees of separation is 1 because they acted in that movie together. You go through that one single movie, and that's their degrees of separation. And if they were both in a movie with a third actor, then we would have... Oh, man. I don't know why I struggle with this. But if 2 actors are in a movie, never in a movie with each other, but they're both in a movie, different movies with a third actor, then the degrees of separation would be 2, because they go through that third actor through 2 movies to be able to get to each other. And that would be their degrees of separation being 2. And this is often a game people play, the degrees of what happened there? The degrees of Kevin Bacon. So any actor, you can determine their Bacon number by how many movies you have to go through to get from them to Kevin Bacon. So how many actors or how many movies do you have to go through to get from one actor to another? So that's what we want to do. We're going to see in lecture today that this is going to boil down to finding their distance in a graph, and we're going to use breadth first search to determine that. So all of the degrees of separation is to say, can you find the distance between 2 nodes in a graph? And throughout the whole lecture, I'll show you exactly how to do that with the homework. And one edge case, the 2 edge cases, I guess, the degrees of separation between an actor and themselves is 0. And the degrees of separation, if there is no path between 2 actors, is -1. So we'll use -1 as kind of our error code. If we see -1, that means those 2 actors are not connected at all. There's no possible path of movies that you can traverse to get from one actor to another. And that's what we want to build for this one. It's I like these types of homeworks. We're kind of... enough stuff that we can have more complex homeworks that are simpler, aside from me struggling to get the exact explanation of what degrees of separation is. The assignment is really one method. So here's this one method, compute the distance between actors, and that's it. We have no testing utility method. The method that you're writing returns an int. So the only testing utility method that would make sense would be take 2 ints and return true if they're the same, false otherwise. Like there's no testing utility method that would really make sense here unless I change the homework entirely, change the task entirely. You do still have testing requirements. And like I said, you can either use files or just manually create your array lists for this one. And with your testing, one of the big hangups with this is making sure that you have some pretty tricky test cases for your code to handle. So making sure that there are test cases where there are multiple paths of different lengths between the two actors that you're using for your test case. If there's only one path, any broken-ass code is going to find that one path. But once there are multiple paths and you have to find the shortest one to actually get their degrees of separation, that gets more interesting. Now you're actually testing the code, which has been a conversation all semester. Like, make sure you write test cases that actually test your code. Like, and I mean that by put your code to the challenge. Like, you shouldn't give it really softball test cases because you could have tons of bugs then. You can have really crappy code that gets all the softball test cases. Write test cases that are really tricky, something that that a lot of bad code would not be able to handle, and that's multiple paths for this one. So if you don't have multiple paths, I have a feature that I'm checking for that makes sure you have some pretty tricky test cases. And then the programming requirements. At this point, I'm fairly, aside from that one case that I just said, the multiple paths, and that I'm checking for that feature, I'm fairly backed off on the testing requirements. So this one, more so than any other task, it's common to see failing my tests in the programming requirements even after you get the testing requirements. Because at this point in the semester, like, you should be pros at testing by now. You shouldn't need any guidance with testing. You should be able to know how to write some really, really good test cases for your code. You shouldn't need Autolab saying, hey, you didn't test good enough. You need more tests. So you shouldn't need that anymore at this point. If you do still need that, you may have missed the point, and you'll get errors in your programming requirements for this one. And again, the point is, like, you're not always going to have somebody forcing you to write tests, and you certainly won't always have somebody checking your tests for coverage the way Autolab does right now. So Autolab has to back off so you have those skills, to make sure you have those skills, because going into 220 and 250 even, you're going to have those skills. They still do check some of your testing, so it's not 100% backed off by then. But after 220 and 250, I'm not aware of any course that's going to check your testing and make sure that you're actually testing things. I've been dabbling a little in CSE116 just because once students aren't forced to test, most of them don't. And then they have issues because they're not testing. So I might remind you in 312, but after 220, 250, nobody's really checking your tests. Even in 312, I won't actually check your tests. But I don't want to get sidetracked on this. But I might make it a requirement of office hours. If you have an office hour question and you don't have tests, we might not answer your questions anymore. So it's still not required. But if you're struggling, anyway. So that's the one. Phase 1 is kind of done. There's no utility method. So this is basically 3 phases. I left phase 1 here and just said no requirement. So that's the last homework. We need degrees of separation based on actors in movies. Let's figure out how to do this. Download this. And I'm going to download all 3 of these. I don't know if I'll go through the third one. I might leave it up to y'all if I go through the third one. The third one is just a memory diagram. And since you don't have any memory diagrams, you never have to write a memory diagram on graphs. It's only there to help you understand how the graph code works, and I don't really know how helpful it is or how necessary this really is. Plus, this graph works in a different way than the graph that you'll use on your homework. So I might leave that up for a vote, what we do at the end here. If we cover something else, if we end early, I don't know. So if you have opinions on that, let me know by the time we get there. But I do know I'm going through the first 2 slide decks. We're definitely going through these ones. So let's do that. And what I'm checking over here, there's a lot of the class starting to fall behind at the end here. So hopefully y'all are able to get caught back up. There's a lot of no submissions for task 7, which we already hit the expected deadline of. So getting a little worried. I'm not going to panic yet, but a little worried that some of you are starting to fall off at the end here. So if that describes you, make sure you get your shit done. No, there's only 6 people watching right now. Not many of you are even hearing me right now. Hopefully you're not watching lecture because you're doing your homework, but even then, like, I don't know, you gotta watch lecture at some point, because today's how I'm telling you how to do task 8. Doing task 8 without lecture is, I don't know, very difficult, next to impossible, unless you've studied graphs in breadth first search already. But even then, there's some 116 specific stuff in there. All right, so let's talk about data structures. Let's do a recap since we're about to learn graphs, our last data structure. And for those of you who have taken or are taking CSE191, a lot of the beginning here is going to be review, but I gotta introduce graphs for those of you who have not taken 191 yet. So I am going to assume that you know nothing about graphs. So if that isn't true, you kind of have a little bit of chill time at the beginning until I start talking about breadth first search and how we use that to find degrees of separation. So let's introduce graphs first by talking about the data structures we have and why we even need another one. Why do we need a 5th data structure? We already have 4 perfectly useful data structures. So first we have our sequential data structures. These are the data structures where the order matters. We just have a whole bunch of values and they're stored in a specific order. That's our array list and our linked list. These are our 2 sequential data structures that we have. It was list in Python, it went by different names in different languages, what we actually call these things, but in Java it was array list and linked list are 2 data structures there. Then we had key value stores, where instead of storing values in a specific order, we're mapping them to keys. So we have keys that are mapping to values, our key value store, or our mapping data structure, which in Java is a hash map, was what we used anyway. By the way, there are others. There's a tree map, which actually combines these 2 in Java. But the one we used was hash map for Java. And then we introduced a tree, our first nonlinear data structure, where we have some actual structure in the nodes based on how these nodes are stored in memory and how they refer to each other. We have this branching property. This allowed us to represent data in a different way than our previous 2. Our first one is storing a sequence of values. Our second one is storing a mapping of keys to their values. And then a tree is our first structural difference. We have some meaning in the structure of these things. And we use it to build a binary search tree to take advantage of that structure to be much more efficient, get our log n sorted values. Log n operations on sorted values was the usefulness here. But there are others. We didn't go over other applications of this, but there are other ways to take advantage of this structure for specific applications that make it very useful. All right, so why do we need another one? Why do we need a 5th one? And the reason is there's some data that just doesn't fit into any of those other data structures. So any of these examples of the subway system in New York, where we have stations with rails connecting them, and we can have, importantly, loops in here. Any intersections and roads, any road system. So we have intersections that are connected by roads, and not all intersections are connected to each other. And the example that we'll look at throughout the lecture today is the early days of the internet, the nodes of the internet that are connected to other nodes in the internet, or other servers, routers, these other locations that are connected through cables to be able to create the early days of the internet. I think it was ARPANET when at the time of this diagram. It wasn't called the internet yet, but the early days of the internet is the example we'll use. So with data like this, how do we represent our data? And the first thought that I would think of, at least, is to use a tree for this. If we have to use one of our existing data structures, I would try using a tree where each node has child nodes for each other node that it's connected to. So UCLA is connected to Stanford, SRI, UCSB, and RAND. So I'll create a node for UCLA and just picking a node, at randomish to be my starting node. I'm going to start at UCLA, or my root node since it's a tree. And then have, instead of a binary tree where it has 2 child nodes, we're going to have any number of child nodes. So I have 4 child nodes here. And then Stanford, just repeat the process. Stanford is connected to SRI and UCLA. So it has child nodes of UCLA and SRI. And right away we start seeing the problem here. So Stanford has UCLA as a child and UCLA as a parent. Now UCLA is going to have Stanford as a child, which has UCLA as a parent, and we're just going to keep going infinitely here. We also have SRI, so maybe you say, well, you don't add a child if it's your parent node, but we also have the problem with SRI. SRI is not Stanford's parent node, but we do have it as a child node in the graph, so now we have to look through the whole tree. I haven't introduced graphs yet. The whole tree. So we'd have to look through the whole tree and look for those nodes to not add the duplicates, but then we lose the information of this edge. We kind of need a child node that goes over to SRI, to the existing SRI, and then not add the duplicate nodes. So it gets a bit tricky to go with the tree here. And even if we do, that last idea is the one we're going to go with, by the way. Even if we do, remove the duplicates, we say, okay, if we have a reference to an existing node, just add an edge to that existing node, and then build your tree like that. This is okay. This isn't quite what we want. I mean, it kind of is, but there's one big problem here. Is we're going to run our tree traverses. We say, okay, I got my tree. Now let's traverse this tree using one of our traversals. Let's use a pre-order, in-order, post-order. Let's use one of our traversals. We'll start at UCLA. We'll go through all the child nodes. It's not just left then right, so let's just go through all of them for recursive calls. We do the first recursive call, Stanford, and maybe we can have some code that says don't go back to your parent node, which would be kind of tricky to code, but we'll at least go to SRI, make a recursive call to SRI. SRI is going to make a recursive call to UCLA. UCLA is going to make another recursive call to Stanford. And as soon as we hit one of these loops, we're going to go infinite because we have what's called a cycle or a loop. I called it a loop right there. But we have cycles, which are paths from a node back to itself. So we have a cycle right here, or a cycle right here, or a cycle right here. We have lots and lots of cycles in this graph, which we never had in trees. At least we're very careful not to have them in our trees. Now we could have a node further down a tree that has a reference as one of its left or right child nodes, a reference back to the root of the tree, and add that cycle, and then our algorithms go infinite. Because we didn't always end up at null, so there was nothing to end the recursion. We could break our trees in the same way, but we were very careful not to do that. Same with our linked lists. If we don't end at null, if instead of the last node being null, it has a reference to a node that's earlier in the list, we go infinite. Everything breaks. We got a cyclical linked list. Big problems that happen when we have that. So we were just very careful to avoid those situations with those data structures. But with graphs, when we have data that looks like this, that naturally has cycles in it, where that's the actual use case, is we want cycles. We have cycles and we want to represent this data. We're going to need a new data structure, and that data structure is graphs. And it is going to look like this. It's going to, this is the structure of the data that we have. But we have to figure out how we're going to represent this and how we're going to traverse this data without getting stuck in infinite loops. So we need new sets of tools to be able to work with data once we can have cycles in our node-based data structures. So we're going to introduce graphs. Graphs, this is a graph. It is similar to a tree, but we can have cycles. We have to avoid that infinite recursion, and there are not necessarily any leaf nodes to be able to end that recursion. There could be, like this could be in the structure of a tree. It's one of those things where every tree is a graph, but not every graph is a tree. You can have a graph that just doesn't happen to have cycles, and it's technically a tree. But we can't guarantee that. Our graph algorithms have to can't assume that there are always going to be leaves to terminate the infinite recursion. A leaf, just as a reminder, because I didn't use this term very much. A leaf node is a node, a binary tree node or any tree node with no child nodes. Oh, I do have that reminder right here, actually. So the way we represent a graph is going to be a little different than our linked list and our trees also. Our linked lists and trees, we had a node class, and that node class knew the references to other node objects when we created objects of that class type. We're not going to do the same thing with graphs, so we're not going to create an object on the heap for each one of these values. Instead, we're going to have one graph object that's going to store a list of the nodes and edges. So nodes and edges is how we're going to represent graphs, where each one of these nodes, which is what we call them in linked list and trees, each one of these nodes is going to be stored in a data structure, and then we're going to store each one of these edges that connects to nodes in a data structure, or rather data structures. We're going to store all the nodes and edges for the graph. And whenever you learn about graphs, which is now in 191, in CSE150, in 331, at a minimum in those 4 classes you're going to learn about graphs, assuming you're going down the computer science degree path. Every time you see graphs, it's all about nodes and edges. Nodes and edges. That's how we represent graphs. And there's a few different ways to actually represent these nodes and edges. How do we actually store these? And it's going to depend on certain applications. What's your specific goal? Why are you storing a graph? And there's going to be 2 major ways that we're going to see. I'm only really going to talk about one today, but I will at least mention the other one. The one we're going to use in 116 is called an adjacency list, where we're going to store for each node a list of all of its neighboring nodes. So UCLA, I'm going to store for UCLA a list of all of the nodes that are connected by an edge to UCLA. So here's UCLA and all of the nodes that are connected by an edge to UCLA, which we call neighbor nodes. And if you're looking at this and you're like, well, that looks like a map, then you're absolutely right. This, in your actual code, this would be a hash map of nodes to array lists of nodes. And that's how we'll represent our graphs in CSE116. So it's actually not a new data structure. I mean, it is, but it isn't. It's a combination of existing data structures. We're going to use an array list and a hash map, combine the two to represent our adjacency list, which stores all the information for our graph. So we're taking things we know, combining them, and kind of creating something new out of existing stuff. Which is why I'm not sad of losing a graphs memory diagram, because we did link array lists, we did hash map, although I didn't assess you on them. I realized kind of after the fact, I never put either of those data structures on the midterm, so you didn't actually have to use either data structure in your memory diagrams. But you did in 115, so I'm still comfortable with that. You were already assessed on it in 115. You should know how to do that. In theory, if you were able to do it back then, you should still be able to do it now. I realize that's not always flawless, unfortunately. But but at least you were assessed on it at one point. At one point in your life, you did, unless you transferred in to take 116 and didn't take 115 here, or you took 115 longer ago. You should have been assessed on that. Or maybe I should have just put it on the midterm. Okay, so... the other way of representing these. I want to at least mention the other way of representing them, because you'll see it in other classes, is called an adjacency matrix. And that's where you have a 2D data structure. For our purposes in Java, this would be an array list of array lists. And each array list, for each pair of nodes, so I think of this as like a spreadsheet where the rows are nodes and the columns are also nodes, and then you have a Boolean value for each cell in that table, and that value is 0 if there's no edge connecting those nodes, and 1 if there is an edge connecting those nodes. So you represent every possible edge and then put true or 1. Or I said Boolean and then I said 0 and 1, didn't I? You put true if there is an edge connecting them, and false otherwise. Yeah, so the adjacency list, like this is saying there is an edge between UCLA and Stanford. There's an edge between UCLA and SRI. There's an edge between UCLA and UCSB. And there's an edge between UCLA and RAND. And for what it's worth, every edge is represented in this adjacency list twice. So Stanford, if we go down to Stanford to UCLA, UCLA to Stanford, that edge connecting UCLA and Stanford is represented in this twice. So no matter what edge you're looking at, you can easily find all of its neighbors very quickly with the adjacency list. So it contains every edge twice, and by getting just the keys out of this, you have every node as well, every node in the graph. There's one kind of edge case. That's something we really have to worry about in the homework, at least. In the way that we represent graphs, once we get to the code, if a node doesn't have any edges connecting it to any other nodes, it won't even make it into the adjacency list, for what it's worth. But that's more of a situation of the code. But if like an actor isn't connected to any other actors, their degree of separation between themselves and any other actor is always going to be -1 anyway. So we have to handle that situation, but knowing that they're not necessarily going to be in our adjacency list. But it does contain every edge, and in fact, every edge twice. And here's our code. Here's our graph that we're going to use. So the adjacency list. So we have a type parameter, of course. We want to store any type of values. We're going to store strings for this one. It's also going to be strings in your homework, so I'm not pulling any punches here. It's just we're only going to see graphs of strings. Unless you want to create a graph of something else on your own volition, that's fine. But it's always going to be graphs of strings. Just happen to be the lecture example that we created, happen to be the homework that we created. It's all strings. So we're going to create a graph of strings, and the adjacency list is a hash map of those strings to array list of strings. So for each node, the adjacency list is going to store for that node an array list of all of the neighbors for that node. The constructor is just initializing the hash map. This instructor could be completely gone, and we could initialize it right here if we wanted to. It's not much going on there, just initializing our data structure. And then add edge, add bidirectional edge. I'll tell you right now, add bidirectional edge is the only one you'll need for the homework. We're always going to have what's called bidirectional edges, which means you can traverse the edge in either direction. So when I add UCLA and Stanford, I add an edge. That means I can go from UCLA to Stanford and Stanford to UCLA. Add edge is if you want to add a directional edge, which means it's a one-way trip. You could only go from UCLA to Stanford and not vice versa. So add edge just doesn't apply to what we're doing on the homework. Add bidirectional edge, this is what we want. We want to add that edge in both directions in our adjacency list. So when we add an edge between two nodes, we're going to lazily initialize the nodes. This is where, I mean, if we never add an edge for the node, then the node never makes it into our adjacency list, for what it's worth. So we're going to add both nodes. When we add a node, we're going to check if that node exists in our adjacency list. If it does not exist in our adjacency list, initialize it. So we're going to add it to our adjacency list, create a key that maps to an empty array list for that node. But if it was already existing, if it already exists in the adjacency list, we want to make sure we don't reinitialize it. So we don't want to wipe away any edges that already exist for that node. So we're just going to do nothing. If it already exists, don't do anything. So add node is going to initialize the array list the first time we add an edge containing that node for each of the nodes. But after it's already created, already initialized, it's not going to do anything. And then we're going, oops, I'm pointing at the wrong ones. And then we're going to add this edge into our adjacency list. And since it's a bidirectional edge, we can traverse it in both directions. If we ask node 1 for all of its neighbors, it better include node 2. If we ask node 2 for all of its neighbors, it better include node 1. So we're going to add it in both locations. So for both nodes' adjacency lists, we're going to add the other node to it. So when we add UCLA Stanford, we're going to add Stanford to UCLA's adjacency list and UCLA to Stanford's adjacency list. And same thing for all of these. We're going to add that node to each, that edge to each node's adjacency list. So BBN will now have Harvard listed as a neighbor, and Harvard will have BBN listed as a neighbor in the adjacency list. And that's our graph class. Like, this is the extent of the code that I'm going to show today. And if this is relevant to you at all, in the 11 a.m. lecture, in the next lecture, I don't even think I'm gonna do code. I think I'm just gonna do the slides because, like, this is it. This is the code. Maybe I'll code this part live in 11. I haven't quite decided yet if I think there will be value in that or not. But I'm leaning towards not, because I would do the rest of the lecture. I'm doing the rest of the lecture in the slides anyway, so I might not. I might do the same exact lecture. Okay, so let's get another definition out there. A path in a graph is a sequence of nodes that are all connected by edges, where each consecutive pair of nodes is connected by an edge. So this path, UCLA, SRI, Utah, MIT, BBN, RAND. Let's check our graph. UCLA to SRI, there is an edge between them, so we're good so far. SRI to Utah, there is an edge. Utah to MIT, there's an edge. MIT to BBN, BBN to RAND. So there was an edge connecting every consecutive pair of nodes. So this is a valid path in the graph. SRI, Utah, BBN. SRI to Utah, there's an edge. Utah to BBN, no edge, not a path. So a path is a sequence of nodes that are connected by edges, which is, I think, a pretty intuitive definition. I think I can rip through that one pretty quick. It's a pretty intuitive definition. If we think of our intersections as nodes and roads connecting intersections, that would be a list of intersections that are all connected by roads. If there's no road connecting two intersections, you can't drive between them. It's not going to be a valid path for you to travel to get to your destination. Okay, actually I'll pause. I don't do this much with the stream delay, but I'll pause for questions for a bit here, just a little bit, and wait, because this is, like, that's graphs. That's it. Just like when we did linked list or trees, introducing the structure of the data structure doesn't take horribly long, not in 116 at least, when we're not analyzing the runtime and efficiency of it or anything. Just introducing the data structure is pretty straightforward in this. It's the algorithms that we use on that data structure that take a bit longer, and that's breadth first search. We're going to spend the rest of the lecture talking about breadth first search. And like I said at the top, we will have a little slack time at the end. So if y'all have questions about anything, we can use that time to answer questions. Or if you do want to go through that memory diagram. But I am going to leave it up to y'all. Once I get to the end of the second set of slides. I'm going to leave it up to y'all as to what we do after that. If you want to see the memory diagram, you have questions about presumably another task or task 8, I'd be happy to go through that. You shouldn't really have questions about task. I mean, maybe you'll have questions about task 8, but after today's lecture, today's lecture is all about holding your hand and walking you through task 8. So if there are questions about task 8, it would be questions about the lecture itself. But if you're stuck, like I said, a lot of y'all didn't finish task 7 yet. So if there's something, no, you're not. Yeah, but you're not getting stuck on task 7. Most of the students who have not completed task 7 haven't even submitted task 7. So it's not like they're stuck on task 7. Which is concerning because the expected deadline already passed. But hopefully everyone can make it across the finish line at least. Okay. No questions. I rambled long enough for the stream delay. Let's just keep going then. So a graph is connected if there exists a path between any two nodes in the graph. So this graph is connected. No matter what node we start at, we can get to every other node in the graph. But what if we change this graph just a little bit? I'm going to remove 2 edges that used to be here. Now this graph is no longer connected, and we have what's called 2 connected components. We have one connected component here and another connected component here. And my question is, how would we find these connected components? Or how do we even know if 2 nodes are connected? If I give you 2 nodes and I say, are these 2 nodes connected? How would you even figure that out? And this is like the first edge case of the homework. How do we even know if 2 actors are connected to each other? Is their degrees of separation infinite or not? Should we return -1 or an actual number representing their degrees of separation? And the next slide deck is how we'll actually find that number for the degrees of separation. But first, an easier question, how do we tell if they're even connected? How do we even know that? And with this graph here, pretty straightforward. We're going to use our eyeballs and just see. If I give you any 2 nodes, if one of them's in this connected component and the other one's in this one, then they're not. Otherwise, they are. But the internet's gotten quite a bit bigger since the early days. We have a huge data structure, and you're no longer going to eyeball this one. You're not going to be able to just say, well, you gave me this one and this one. Yeah, it looks like they're connected. You're not going to be able to do that once the data is big. And that's the general conversation about data structures and overall is what happens when you have a lot of data. Data structures are, dare I say, useless when the data is small. If this is your data, why even bothering? Just stuff it in an array list in whatever format you want to store this information in, and write your algorithms manually, or don't even write algorithms. You don't even need a computer if this is your data. Computers, and I won't even stop at data structures. Computers are only useful when you have a lot of data. If you don't have a lot of numbers that need to be crunched, that's the only thing a computer does really well, is crunch a lot of numbers extremely quickly and with 100% accuracy and 100% memory. I mean, aside from hard drive failures, the computer is 100% accurate even when computing over billions, trillions of values, and can store the results perfectly. That's what a computer's strengths are. That's what it does well. So if you don't have a problem that fits those strengths, why are you even using a computer? If this is your data, you would just do this with pen and paper. You would work with it. Just jot it down. Here's my graph, okay, and answer all your questions just by looking at the graph without a computer. Why waste your time writing code if this is your data? But once you have lots of data, this is where we really need computers, and we need computer programmers. We need software engineers. This is where the problems get interesting. And this is where we need to choose the correct data structure for the problem, which is mostly 250 topics telling you how to choose each data structure. 116, we're just introducing, here's 5 data structures in that neat. 250 is going to say, okay, here's where you use a graph, here's where you use a tree, here's where you use a hash map, Here's where you can just use a linked list or an array. But that's where things get interesting, is when we have lots and lots of data. Lots of numbers that need to be crunched. Okay, so we're going to use this graph for our lecture example, but don't get bogged down on, well, I can just look at the graph and figure out the answer, because you're not always going to be able to do that, or else we wouldn't have jobs. Like, I wouldn't be able to teach computer science, because no companies would need computer scientists if this was always our data. Okay, so let's learn breadth first search to know how to work with any graph of arbitrary size, to work with the huge graphs, as well as this toy example that we have for lecture. So in the crux of breadth first search, choose a starting node, and then keep searching the neighbors of that node. So I'm going to start at UCLA. Then we're going to explore all the neighbors of it. And to do that, we're going to look at the adjacency list. We're going to pull all of the nodes that are adjacent to UCLA in our adjacency list and explore all of those nodes. So my green box is all the nodes that I'm exploring. And I'm going to go through all of the nodes that I just added, all 4 of these nodes, and repeat the process. I'm going to explore all the neighbors of these 4 nodes. And importantly, I'm going to check if it's already been explored. So when I check Stanford and I have UCLA and SRI, UCLA and SRI are both in my green box already. So I'm not going to do anything when I visit the neighbors of Stanford. But when I visit the neighbors of SRI, I'm going to explore Utah, Rand, I'm going to explore SDC, UCSB, all of its neighbors are already explored, so I'm not going to do anything. Because I have to make sure I don't end up in those infinite loops. So I have to make sure that I don't revisit a node twice. But when I visit the neighbors of UCLA, I get Utah and SDC. Then I'm going to visit the neighbors of Utah, which have both already been explored, and visit the neighbors of SDC, both of which have already been explored. So whenever I have a round of visiting neighbors of the newly explored nodes, and no new node was added, then I know I'm done. That's it. That's the end. And I found the connected component of UCLA, which is the connected component of no matter which one of these nodes I chose as my starting node, it's the connected component of that node. So I have one connected component of the graph, and I see that I have some nodes left over here. So I know that this graph is not connected. And if I was asking, okay, are whatever 2 nodes connected, UCLA and whatever other node, are they connected? Well, if I ran breadth first search on UCLA and I explored that other node, then they are connected. If I did not explore that other node, they're not connected. So when you're asked to create compute the degrees of separation between 2 actors, you're going to start at one of those actors, run breadth first search, and if you've never explored the other actor, then they're not connected and you're returning -1. And I should come right out and say this. I'll do this again at the end of the next slide deck. But for your homework, you're creating a graph and running breadth first search. Those are your 2 primary goals. So you're given the movie data. With the movie data, every actor in any of those movies is going to be a node in your graph. And there's an edge between 2 actors if they've been in a movie together. So for each movie, you're going through every pair of actors in that movie and adding an edge to the graph for each of those pairs of actors. Do that for each movie. Now you have your graph. And once you have your graph, where your actors are nodes and edges between them if they've been in a movie together, then we can start running breadth first search to learn information about the degrees of separation between 2 actors. So you're creating your graph and then using breadth first search on that graph, and that will give you exactly the degrees of separation. We haven't seen how to do that yet, but it's going to end up giving you exactly the degrees of separation between 2 nodes. Then you return whatever breadth first search told you to return. I'm going to skip this slide. This is like a preview. When this is a Monday lecture leading into the Wednesday lecture, this is a preview of the Wednesday lecture. But I'm about to give the Wednesday lecture in its entirety, so I don't really see a point in previewing it. But we're going to talk about how to actually implement breadth first search in our code, what extra data structures to use, and how to get the job done. Which I really like. Graphs is the perfect capstone of the data structures conversation in 116, because you're going to see that we're going to use a lot of data structures. We already used array list and hash map, and we're going to use a bunch more. Okay, so now we're in the next slide deck, the Wednesday, what would be the Wednesday lecture, and let's get a few more definitions out there. We already talked about paths. So a path is a sequence of nodes in a graph. We have the path Lincoln, MIT, Utah, SDC, Rand, UCSB, SRI. This is a valid path from Lincoln to SRI in this graph. And let's introduce the length of a path. The length of a path is the number of edges in the path, or the number of nodes in the path minus 1. Either one is going to give you the same number. So this path has 6 edges in it, 7 nodes. So this is a path of length 6. Distance between two nodes is the length of the shortest path between those two nodes. So we just saw a path from Lincoln to was it Lincoln to SRI? Oh yeah, it was. From Lincoln to SRI of length 7, but that was not the shortest path from Lincoln to SRI. The shortest path, or at least a shortest path, from Lincoln to SRI is length 3. We can go Lincoln, MIT, Utah, SRI of length 3. So the distance between Lincoln and SRI is going to be 3, because try as we might, we're never going to find a path of length 2 or 1 between Lincoln and SRI. 3 is the shortest path we're ever going to find, so the distance between those two nodes is 3. Rand and BBN, these are connected by an edge. If they're connected by an edge, the shortest path between them is taking that edge. So the distance between Rand and BBN is 1. And the distance between a node and itself is defined as 0. That's the part of the mathematical definition of distance. A node and itself is going to be 0. So distance in a graph is going to be exactly the degrees of separation in your homework. So your task boils down to creating that graph of actors where there's edges if they've been in a movie together. Given that graph, find the distance between two actors. So your goal is find the distance between two nodes in a graph. Create the graph, find distance between two nodes in that graph. That's what task 8 is those two tasks. And since we give you the graph code, building the graph isn't overly difficult. You do have to loop over pairs of actors, which I have seen students struggle with. I'd argue that, I don't want to argue about it. I'd argue that that's easier than the other part of the homework. I can say that much pretty safely. But find the distance. Once you have the graph, find the distance between the two nodes. That's the bulk of task 8. How do I find the distance between two nodes? So let's learn how to do that. That's what we're going to do for the rest of today's lecture. And again, I'll leave it up to you all what we do after that. I don't see any suggestions yet, but when we get there, I'll ask again. I'll wait for a while. I'll stare at my screen and wait for suggestions. Maybe I'll just stare at my screen until 10:30. All right, so we're going to use, actually, left to my own devices, I'll probably go through that memory diagram, to be honest. So what we want to do is use breadth first search to find the distance between two nodes. That's how we're going to find distance, is with breadth first search that we just went through very briefly, how to use breadth first search, but we're going to do it a few more times. We're going to go through breadth first search 3 more times in this lecture, and each time we're going to add more and more detail It's actually the second to last one is going to be the most critical one for the homework. So let's analyze breadth first search again. Still in a little bit of abstract mode for this one, but we're going to add a little bit more structure to the breadth first search run, because the first time I say explore the neighbors, and explore the neighbors of the neighbors, and explore the neighbors of the neighbors of the neighbors, it doesn't really tell you how to turn that into code. So let's get closer to that. It's still going to be a little abstract for this one, though. So let's see. Let's run through this again. And I'm going to start at Carnegie for the next 3 runs of the algorithm. I'm going to start at Carnegie this time. And now, instead of just saying explore the neighbors of the neighbors, we're going to do that, but we're going to create a new graph containing all the edges that we've used to traverse the graph while running breadth first search. So we're going to add Carnegie, that's our starting node, and we're going to add that up at the top. And every time we explore a new node, we're going to add those edges that we used and draw them visually lower on this new graph that we're creating. So Carnegie found Case in Harvard. Case is going to find Lincoln. Harvard's going to find BBN. And just keep doing this as we go through the process, adding only the edges that were used in the run of breadth first search. And we have a little bit of ambiguity here. Lincoln and BBN can both explore MIT. Like Rand is definitely going to be found by BBN, so we're going to see Rand right here. But MIT could either be off of BBN, found by BBN, or found off of Lincoln. So I had to break this tie for the slide, at least I had to break this tie arbitrarily, and I decided to give MIT to Lincoln. For our purposes of degrees of separation, whenever you have a situation like that, no matter which one is chosen, it's going to give you the same answer, the same degrees of separation. For example, Carnegie to MIT going through Case and Lincoln, or Carnegie to MIT going through Harvard and BBN, those are both paths of length 3. I can't even count. Those are both paths of length 3. So no matter which path we choose, we're still finding a path of length 3, which is a shortest path from Carnegie to MIT. So sometimes you will have ties. You have 2 paths of length 3. The distance between Carnegie and MIT is 3. So we are still finding one of the shortest paths. It doesn't matter which shortest path we find when there is a tie like that. As long as we find one of them, we're going to be okay with that. We're going to be good with that. Then MIT is going to find Utah. Rand's going to find 3 separate nodes. So we're going to add all those to our nodes. Again, always going down visually on the slide. SRI has a 3-way fight over it. I forget which one I gave it to. I think I gave it to Utah. And then UCLA is the only one that can find Stanford here. Okay, so we ran through breadth first search again. We were a little more careful about the details, and we created another graph with only the edges that were used by the algorithm to explore new nodes. So any of these edges that are left in white, these ones didn't make it into the second graph here of all of our nodes. And we can see that the second graph is a tree. It has the structure of a tree, as in it doesn't have any cycles. It's represented as a graph, technically, the way I described it. I guess we didn't write the code, so it doesn't have to be a graph. But it could be a graph, but it is a graph that is also a tree because there's no cycles. And we can think of Carnegie as the root of the tree, and it's not a binary tree. We do have a node with 3 child nodes, so it's not strictly a binary tree with just left and right. It can have, say, an array list of child nodes for this graph, or for this tree. And when we look at this tree, the way we built the structure is we can notice that there are levels to this tree. So if we think of the starting node as level 0, and each time we go down exploring a new node using a new edge, we add 1 to the level. So this is level 1, then 2 away from the starting node is level 2, level 3, level 4, level 5. Then the level number that we have for a for nodes, the level number is exactly the distance from the starting node to that node. So by running breadth first search in this way, we can find the distance from the starting node to every other node in the graph. So we can look just by the properties of breadth first search, by the way breadth first search works. I know that the distance between Carnegie and Stanford is 5 because it ended up on level 5. And if there was a shorter path from Carnegie to Stanford, it would have found that earlier. It would have found the path by taking all of the edges, which is all the neighbors of Carnegie. This is clearly all of the nodes of distance 1 because it's all of the nodes that are connected to Carnegie by an edge. So that one's clear. But after that, it gets a little cooler. We get to take advantage of this property. All of the neighbors of the neighbors are going to be all of the nodes at level 2. Their neighbors are going to be level 3. Like if, say, Stanford, there was a path from Carnegie, Harvard, BBN, Rand to Stanford, then there would have been an edge from Rand to Stanford, and Stanford would have ended up on level 4. So the fact that it ended up on level 5, that it took 5 rounds to get to Stanford, that means the distance between Carnegie and Stanford is 5. And I can stare at this graph all day. I'm never going to find a path from Carnegie to Stanford or Carnegie to SRI that's shorter than 5 edges. I have to traverse at least 5. Now I can go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. There are multiple paths of length 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There are a lot of paths from Carnegie to SRI of length 5, but there's no paths that are going to be shorter than 5. There's no possible way to get there in less than 5 edges. And same for Stanford, but Stanford, there's only one path to get there. 1, 2, 3, 4, 5. There were no ties that were broken to find this one. With SRI, there were a bunch of ties that were broken, which meant like SRI could have been explored by Utah, UCSB, and UCLA, and Utah itself could have been explored through Case and Lincoln or through Harvard and BBN. So that's why we have so many different paths there. It's all those ties that we broke. They were all tied for the shortest path from Carnegie to SRI. So this is how we can find distance between any two nodes. You have your two actors. You got to find their degrees of separation. You start at one of those. Doesn't matter which one, but you choose one of them as your starting node. Run breadth first search, keeping track of these levels. And then the level of the other node is going to be your distance number. If you've never explored the other node, well, the distance is -1. It's mathematically it's infinite. You have infinite distance. We're representing that with -1. Since it's integers, we don't really have an infinity, which is fine. I mean, that's good and all, but how the hell do you code that? Because when we were going through that example, a lot of the time I said, well, just draw the nodes that you're exploring visually lower on the slide. How in the hell would you do that in code? How are you going to put something visually lower in your code? Like what line of code do you write to do that? I don't know. We would use like image recognition and all kinds of crazy stuff, visuals, and we're not doing any of that. So what's a more practical way to capture that same information of the levels that we had, but representing it in code? And here's the run of breadth first search that's going to be very important for your homework. I basically walk you through exactly how to do the homework with this run of breadth first search. If you weren't paying attention to the rest of the lecture, at the very least pay attention to this one. And I walk you through pretty much exactly how, I already said that, but pretty much exactly how to do the homework. So for this one, but you got to turn my English sentences into code. That's your task. So for this one, we're going to use 3 separate data structures. So we're going to use 3 data structures in our code. We're going to have one data structure, which is going to track our distances. If this looks like a hash map to you, you're that on a hash map that's going to map nodes or actors in our homework to their distance from the starting node. And there's a few different ways you can initialize this. For the slide, I just wanted my whole data structure here right away. So I initialized them all to infinity just as a visual indicator for the slide. For your homework, what you can do is just not add these key value pairs. You don't have to initialize these to anything. You can just add the starting node and have a hash map of size 1 with just one key value store, and then add in the new nodes as they're explored. So a little bit difference. I mean, if you do want to initialize them all to like integer.max value, that's fine too. In the slide, these are infinity symbols. I always have questions like, what are those? Those are infinity symbols. People think they're like glasses or something. And then we're going to initialize this hash map with the starting node being distance 0. So the node to itself, the distance is always 0. So we're going to initialize that starting node with a distance of 0. Oops. My slides do this out of order of the way I want to explain them. I got to reorder them. So this is a map storing the distances or levels for every single node. So instead of saying visually lower, what we're going to do is every time we explore a node, we're going to add 1 to the distance of the node that explored it, and then update our hash map with those distance values. And the way breadth first search is going to work, the way we're going to avoid revisiting a node a second time. So once a number is added, once a node is added to this hash map and has its value, that is its distance value. That's its final distance value, and it'll never be updated in the map. It'll be added once, and that's the answer for that node. So as soon as we explore a node, we know its distance from the starting node. Second data structure, so we have hash map. Second data structure is a queue. This is the one time where we actually get to use either stack or queue. I guess stack we use in the program stack and memory, so we get familiar with that concept. But this is the one time where we'll use a queue. And this one you will want to use a queue data structure in your code. There are many different ways to do that. You can use the queue class that we created in lecture that's in the examples repo. You can use Java's built-in queue. I'm fine with you doing that. This isn't about the structure of a queue because, well, I gave you the structure of a queue anyway, so it's not like you have to build it. Or you can use a linked list as a queue. You can kind of rebuild your own queue that way. Or you can use an array list as a queue. As long as you have the concept of a queue in your code, that's going to be fine. I'd recommend using one of the pre-built queue classes. Probably Java's built-in queue, if I'm being honest. Because you want to be able to check if the queue is empty, as we're going to see throughout the run of this. And we don't have that functionality in our queue. Our queue that we built in class is a true queue. It has enqueue and dequeue. It doesn't have any slow features. So you would have to add that, which isn't that big of a deal. But a queue. Anyway, the queue is going to track which nodes we're going to visit the neighbors of. So this queue, or whatever's at the front of the queue, that's the next node that we're going to explore the neighbors of. We have Carnegie in the queue. We're going to initialize the queue with the starting node. So we're going to enqueue the starting node, and that's going to be the initial state of our queue that we're going to use to track the nodes that we're going to visit the neighbors of. And then a third data structure, which you really have a lot of flexibility in this one. Most students use an array list. For what it's worth, if you want to use an array list, I'll probably even refer to this as an array list throughout the runtime. Throughout the run of these slides as we're going through the breadth first search run. Some data structure that's going to mark which nodes have already been explored. And this is very important because this is the one that's going to prevent our infinite loops. So we're going to keep track of all the nodes that have been explored. If we have an array list and we use the .contains method, we can check, has this node already been explored or not? The true data structure is probably set, would probably be the best one to use. Maybe. I don't know. Probably a set. Definitely not an array list, though. Probably a set would be the best one to use. Set if you took 191, it's exactly what you would expect from a set. It's a data structure that can't have duplicates in it, and it's very efficient for checking if for finding a node. So if does this set contain this specific node? Very, very efficient at that, which is the one question we're going to ask that data structure over and over again. So it's much faster than an array list, but we're not too concerned about efficiency in 116. But if you are getting sick of your tests taking a while to run, if you're using the entire movies.csv, the tests do get pretty slow if you're using an array list. You will start feeling the pain. If you want to use a different data structure, go for it. Or even a binary search tree if you really want to get fancy with it. But that should be, I believe, Java sets are built on hash maps, which are more efficient for this specific purpose than binary BST. But the set won't store anything in sorted order. But getting into 250 territory there. But anyway, so you have some data structure, probably an array list for most of you, that's going to store keep track of which nodes have been explored or not. And we're going to initialize that with the starting node. So I'm going to mark these in orange. If it's marked in orange, that means it's in that data structure to mark that it has been explored. But you need some way to say this node has been explored. So we mark the starting node as explored, enqueue it, and set its distance to 0 in this hash map. And now we're ready to rip. We're ready to run breadth first search. This is our initial state, and at this point you should enter a loop of sorts. And we're going to loop. Oh, I thought I had a slide there. And we're going to have a loop that's going to run as long as there's something in the queue. So we're going to run until this queue is empty. And each time we execute that loop, what the loop will do is dequeue from the queue. So it's going to grab the node at the front of the queue and explore its neighbors. So we're going to dequeue Carnegie, and we're going to explore each of its neighbors. So we're going to go to that adjacency list. We're going to say, okay, who are the neighbors of Carnegie? Which nodes can I reach from Carnegie by taking a single edge? And it's going to say, well, Case and Harvard are those nodes. So we're going to take a look at Case, and we're going to check. We're going to ask a question. I'm going to repeat this for every single node. We're going to get this down. We're going to check. Has this node been explored? Has this node been explored yet? It has, and at this point it has not. Has this node been explored? No. It has not been explored, so we're going to explore it. Every time we explore a node, we're going to mark it as explored in our whatever data structure you're using to mark nodes as explored, probably an array list. Mark it as explored, enqueue it into the queue, and set its distance value. The distance for any node when it's being explored is going to be the distance of the node that explored it plus 1. So since Case was explored by Carnegie with distance 0, Case's distance is going to be 1. Same thing with Harvard. Has Harvard been explored? No. Mark it as explored, enqueue it, and set its distance equal to the distance of the node that found it plus 1. And that really is it. At that point, we're at the top of we hit the bottom of the loop, we go back to the top of the loop, and we do it again. We do this until the queue is empty. But we're going to do the same exact thing over and over and over again. So we're going to dequeue Case. We're going to check its neighbors. Lincoln is not explored. Mark it as explored. Enqueue it. And set its distance equal to the distance of the node that found it, which is 1, plus 1. So each time you do that, you're going to pull the distance out of this hash map, get that distance of the node that's exploring, that's finding that node, add 1, and then put into your hash map that node that was explored with the updated value, the plus 1 value. And then Case is also going to check out Carnegie. We're going through all the neighbors. We're going to the adjacency list, getting all the neighbors and checking all of the neighbors. We checked Lincoln and did all that. We're also going to check Carnegie. But here what we're going to do is say, have we explored Carnegie yet? And the answer is going to be yes. Carnegie's already marked in orange. It's already in your array list or set or whatever data structure you're using to mark these things as explored. It's already been explored. So what we do is nothing. Nothing at all. We don't want to re-explore nodes multiple times because we will get in an infinite loop if we're doing that, if we're not careful about that. So we want to say, has this neighbor already been explored? It has. Don't do anything at all. So we only actually explore Lincoln. We explore it, enqueue it, set its distance. The front of the queue is now Harvard. So we're back at the top of the loop again. Explore all the neighbors of Harvard. That's going to be BBN. Mark it as explored, enqueue it, and set its distance equal to 2 because Harvard's distance is 1, so plus 1 is 2. Check out Carnegie. Carnegie has already been explored, so don't do anything there. So DQ Harvard, enqueue BBN, mark BBN as explored, BBN is 2. Check out Carnegie, already been explored, don't do anything. And we're back at the top of the loop again. Check out Lincoln. And this is where the ties are going to be broken. So before I said ties are broken arbitrarily whenever there's a tie. But you don't actually have to write any code that's going to handle that at all. Breadth first search, the way I'm explaining this, automatically handles those ties. And the way the ties are going to be broken is based on the order of the edges in your adjacency list, which will be the order in which the edges were added to your adjacency list. That's what's going to end up arbitrarily breaking the ties. It's not something you have to think about. No matter how they're broken, the distances will be the same. If Lincoln explores MIT or BBN explores MIT, either way, MIT is getting a distance of 3. So it doesn't matter which one explores it, because it's still getting the right distance. It's always getting the right distance value. But the way the tie was broken in this case was the order of Carnegie's adjacency list. It was Case and Harvard, just what I chose for the example. I said it's probably going to be Case and Harvard. So Carnegie explored Case first, which meant Case got into the adjacency or the queue first, then Harvard. And then since Case was explored before Harvard, Case was DQ'd before Harvard, which meant Lincoln made it into the queue before BBN. And then Lincoln is going to be DQ'd first, and Lincoln is going to end up finding MIT. So that's how the tie is broken. It was the adjacency list order of Case and Harvard in Carnegie's adjacency list. No extra logic. You don't have to say, if there's a tie, do this, and this is flip a coin or whatever. You don't have to do any of that. Just let it wash out in the way the code's written. So Lincoln is going to explore MIT, mark it as explored, enqueue it, and set MIT's distance equal to Lincoln's distance plus 1. So from your hash map, pull Lincoln's distance, add 1 to it, and then put MIT and that new distance into your hash map. Check out Case. Case has already been explored, so do nothing. Now BBN, when it finally gets to get DQ'd and see MIT, it sees that it's already explored, so it's not going to do anything with MIT. It's not going to enqueue it again. Like we don't want MIT in the queue twice. That's going to really start breaking things. Same thing with Harvard. It's been explored. Don't re-explore it. But that's how our ties are broken. Lincoln got to MIT first. When BBN checks out MIT, it's already explored, so we don't explore it again. That's how we're avoiding infinite loops and all kinds of issues. BBN does find Rand, so mark it as explored, enqueue it, and BBN's distance is 2, so Rand's distance is going to be 3. And we can start seeing a bit of a pattern here. Is the way that we're enqueuing, what the queue is doing for us here is maintaining the proper order in which we're going to visit the nodes. If you watch the runtime, watch things closely, what happens is we enqueue the node of distance 0, the starting node, dequeue that node, and enqueue every node that's going to have distance 1 into the queue. That means every node with distance 1 is going to be explored next. And they're going to enqueue all the nodes of distance 2 Then we dequeue all the nodes of distance 2 and enqueue all the nodes of distance 3. So we're always going to explore the nodes in a non-decreasing order of their distances. We're going to explore all the nodes of distance 0, then all the nodes of distance 1, then all the nodes of distance 2, then all the nodes of distance 3, all the nodes of distance 4. The queue will maintain that order if we're careful about how we're adding the nodes. If we do it the way I'm describing here, we're always going to explore the nodes in distance order, which is what's getting us the actual, which is what's going to guarantee us that we're getting the actual distances for these nodes, because we're not doing things out of order. If we jumped out of order and explored SRI right now, or for some weird reason we got our, we're using a stack instead of a queue, which, by the way, if you use a stack instead of a queue and do everything else the same exact way, you end up with depth first search instead of breadth first search, which is a whole different algorithm, very similar, but a different ordering in which you visit the nodes. The difference is queue versus stack. So now we're going to visit all the nodes of distance 3, and we're going to be enqueuing all the nodes of distance 4 when we do this. So MIT, Lincoln, do nothing. BBN, do nothing. They've already been explored. But Utah, we're going to mark as explored, enqueue, and Utah's distance is going to be MIT's plus 1, so 4. RAND is going to explore SDC, UCSB, UCLA, a whole gaggle of nodes of distance 4. And check BBN and not do anything because BBN's already explored. So mark all 3 of these as explored, enqueue all 3, and all 3 get distance 4 since RAND's distance is 3. Then Utah, DQ Utah, we're about to DQ all of the nodes of distance 4. So we DQ Utah, SDC, explored, do nothing, MIT, explored, do nothing, SRI, not explored, mark it as explored, enqueue it, set its distance equal to Utah's distance plus 1, so this gets distance 5. UCLA, already explored, do nothing, already explored, do nothing, already explored, do nothing. Then Stanford, not explored, mark it as explored, enqueue it, and set its distance equal to UCLA's distance plus 1. So Stanford gets distance 5. And at this point, everything's been explored. So I know that the rest of my algorithm isn't going to do anything. But the way we'll write the algorithm is, as long as there's something in the queue, we're going to keep going through our algorithm. We're going to keep running it. So we are going to keep going. But we know, just because this graph is tiny and we can visually see everything, it's all visually right in front of our faces, we know nothing else is going to happen here. Once we add a distance to our hash map, that is the final distance. So none of these will ever get updated. Everything's been explored. We never unexplore a node. So nothing is going to happen for the rest of this runtime, but we're still going to run through it. Our code's still going to go through its thing and do its thing. So UCSB, we're going to DQ, check SRI, it's been explored, do nothing. UCLA's been explored, do nothing. RAND's been explored, do nothing. SDC, explore the neighbors here. Utah, already explored, do nothing. RAND, already explored, do nothing. SRI, already explored, already explored, already explored, already explored, so do nothing. Stanford, UCLA's been explored, SRI's been explored, so we don't end up doing anything. And now that the queue's empty, now our loop can finally break. We're getting out of our loop and getting back, getting to the next step of the algorithm, which is returning the answer. So we started at Carnegie. That's our starting node. Depending on which node we were asked to find the distance of, say we're trying to find the distance from Carnegie to UCSB, then once the algorithm's done, what we get is the information of the distance from Carnegie to any node in the graph, but we're only interested in UCSB. So we'd go to our hash map, look up UCSB, and return its value, and just return that 4. If UCSB is not in the hash map, or it's in the hash map but still has whatever you chose for your initial value, then return -1. So that's what you have to code for task 8. Create your 3 data structures, initialize them with the starting node, and then go through the queue, DQ, go to your adjacency list, grab all the neighbors, loop through all the neighbors, check if it's been explored. If it has, just move on to the next neighbor, If it has not been explored, mark it as explored. Update your 3 data structures. Mark it as explored, enqueue it, and set its distance equal to the distance of the node that explored it plus 1. And the plus 1 is to account for the extra edge that you had to traverse to find that node. So if I have the shortest path from Carnegie to BBN is 2, and it took me one extra edge to get to Rand, then from Carnegie to Rand must be this distance plus 1. So I can get from Carnegie to Rand with 3 edges. And by the time I'm exploring BBN, I've already found all of the nodes that I can reach using 2 edges. I've already found them all if I'm dequeuing BBN. So if I have an edge to an unexplored node, I know that node can't be explored with distance 2. I know it's not distance 2. I know it's not distance 1 because I already found all those nodes. So if from one edge from a distance 2 node, I can find a new node, I know that node has distance 3. That's the way that shakes down in the algorithm. And that's how to do task gate. I think task gate's one of the easier tests, by the way, just because I hold your hand and walk you through. I basically told you how to do all the code in a little bit of an abstract way. Like, I'm not literally telling you how to write the code, but there's enough information there that any 116, at the end of 116 especially, students should be able to convert that to code. There are some students who struggle with this still. But from everything that I've gathered, all the information I can speculate and everything, I don't think those students watched the lecture. It's like they never have specific questions like, man, I saw you do that in lecture, but I'm just not sure how to turn that into code. That's never their question. They're just like, how? Task gate? What? What is this? So I think this is one of the easier ones unless you skip lecture. But if you're hearing me right now, that doesn't apply to you. This should feel pretty easy to you if you're hearing my voice. If you watched all that. I think what some students do is try to skip lecture, but just look at the slides. They'll download the slides and click through them. And they can get away with that a lot of the lecture. A lot of my slides are meant to be self-contained. But this one especially, like all these slides just say BFS and distance. There's no way you can follow that without my narration. So I think that's the only way students really get into trouble on this one. So those of you who can hear me right now and are actually watching lecture, task gate should be a breeze for you. If not, come to office hours and just say, hey, I saw you in lecture, I saw you do that, and I just, like, this step right here, like, I can't understand what you're saying with that step. I'm always happy to help that. Help you out with that. So if you are struggling, don't hesitate to come for help still. But I do think a lot of students skip this lecture and try to just dive into task gate. It doesn't work like that. Even if they got through tests 1 through 7 like that, it doesn't work for task gate. Okay, I don't see any questions, so I'm gonna keep barreling through. (9:30). We got another hour. Yeah, let's barrel through pathfinding, and then I'll talk about the homework again. I'm still undecided if I want to do that memory diagram or not. If there are no suggestions in chat of what to do, we'll see. We'll see when we get there. We'll see how I feel. I don't think the memory diagram will be particularly useful to you. Is my issue. If I thought it'd be useful, I would do it 100%. I would just plan on doing it. Okay, so that's finding the distance to each node. But what if we want to find the paths to each node? Now this, I don't ask you to do this on TaskGate. Each semester I go back and forth like, should I have them do pathfinding? It is super interesting, but it's also much more difficult than just finding the distance, is actually returning a shortest path between two nodes. And to be honest, it's not that difficult, but the testing for this is extraordinarily, it's a whole new level of testing. This would be a testing utility method and all kinds of stuff added to it if we had you testing pathfinding. So far I've decided to not have you do this, but I still want to explain how to do it, and let you know what you're missing out on, I guess. So for pathfinding, we're going to make one small change to this algorithm. Instead of storing the distance numbers in our hash map, we're going to store the node that discovered that node. So for the starting node, we're going to have some special indicator to say this is the starting node, whether that's null or -1 or whatever you want to indicate the starting node. And then each time a node is explored, we're going to remember the node that explored it. So we got to Harvard from Carnegie. So in this hash map, Harvard is going to store Carnegie. That's the node that came before this node. And I'm not going to run through the whole algorithm the way I did with distance. I'm just going to say that's the one change. Rand was explored from BBN. MIT was explored from Lincoln. So we're remembering which node found each node. And when we go through the whole runtime, the whole run of BFS, we end up with a hash map like this. Each node remembers which node explored it. Not just the distance of that node plus 1, but just remembering the node itself, which is arguably a little bit simpler than the distance, because you don't have to add 1. I don't know. It's about the same effort. They're both super easy when it comes to just inserting into the hash map anyway. But we're going to remember each node. And now here comes the trick. We want to find a shortest path from the start node to whatever node we're trying to get to, and I'm going to choose Stanford for this. What we do is work backwards and start at the end node. We're going to start at Stanford. If I want to find the shortest path from Carnegie to Stanford, I'm going to start at Stanford. That's the end. I know that's going to be the last node in my path. And I'm going to ask Stanford, which node found you? And I'm going to work my way backwards until I get to the starting node. So Stanford was discovered by UCLA. So I know Stanford is my last node and UCLA is my second to last node. And then I'm just going to repeat this process. UCLA, which node found you? Well, Rand found UCLA. So now we add Rand to our path. We'll prepend it to our path. And then go to Rand. Well, which node found you? BBN found me. Add BBN and ask BBN. Well, which node found you? Harvard found me. I add Harvard to our path and ask Harvard. Well, which node found you? Carnegie. Add Carnegie to our path. Carnegie, which node found you? And Carnegie's going to have some special indicator here to say I'm the starting node. Once we see that special indicator, we know that we have our path, and we have our shortest path from Carnegie to Stanford, which happens to be the shortest path in this instance, but we will be guaranteed to get a shortest path from the starting node to whatever node we found. So Carnegie to Harvard, BBN, Rand, UCLA, Stanford. That's the shortest path from Carnegie to Stanford. If we did the same thing with SRI, we would find this path here, which is a shortest path, but not the shortest path, which is what would make testing very tedious for pathfinding. It makes it pretty tricky because you have to, if your code and my correct solution return two different correct shortest paths, you have to accept any shortest path in your test. So you have to identify that it is a correct solution, even if it's not the correct solution that your code returned. It makes it tricky, but this is how we would do that. And then testing gets a little tricky. The way I'll explain how to do that. By the way, to test for that, you would test: does the return path have the length that I expect? So say it's SRI, I'm going to say, did it return a path of length 5? If it didn't return a path of length 5, it's wrong because the distance is 5. It has to return a path of length 5 if we're returning the shortest path between two nodes, a shortest path between two nodes. So if it's not 5, it's done. And then if it is 5, if it's exactly length 5, then check if it's a valid path. If it's length 5 and it's valid, then it has to be a shortest path between Carnegie and SRI in this example. Actually, now that I say it out loud, it ain't that bad. I don't know why students always struggle with that one. I think it's just because it's at the end of a semester and everybody's just so burnt out at that point that that they can't quite think straight. That's my other assumption. But I used to have, it's actually the next thing. I used to have students find shortest paths in a game, and they would have to program the AI to hunt down the player following the shortest path while avoiding walls. So like this AI character right here, chasing the player, the yellow dot, we wanted it to attack the player, but if you just do Euclidean geometry and vectors and stuff, it's going to get caught on this wall right here, get stuck right here, and your game's no fun because the AI is just dumb. So we want this AI character to be able to go around the wall and hunt down the player following the shortest path in this level without hitting walls. And then finding the if the correct solution was actually correct, did it have the right distance, and was every move a valid move? Did it go in one of the 4 cardinal directions between adjacent tiles in this game? And boy, students struggle with that. It is a lot more complex than degrees of separation, to be fair. And building the graph itself was pretty complex with this. But then the testing itself, students really struggle with. Why is the add node method private? Because it doesn't have to be. If you want to make it public and that's the way you want to implement your task gate, that's fine. But it's private because it's only called as a helper method from inside the graph class. So it's only called from the add edge and add bidirectional edge methods. So we don't have, in that graph that's given, we don't have a way to add a node that doesn't have any edges connecting it. Because for our specific application, if there's an actor where the only case that would ever come up is if there's an actor who starred in a film all by themselves. They were the only actor in that film. They didn't have any co-stars or anything. Then they would have a node in the graph with no edges connecting them to any other actors. And that was the only movie they starred in. They only starred in movies by themselves. So their degrees of separation between themselves and anybody else is always going to be infinity, or -1 is what you would return for everything for that actor, except that actor to themselves, which I don't think I ever test for. An actor to themselves where the actor is not in the graph. And you shouldn't test for it either. Let's just not test for that one. I don't even remember what my solution would return for that one. If it would turn 0 or -1. So that situation doesn't come up at all, having a node with no edges. So the only way to get a node in the graph is to add an edge. But yeah, I have no test cases where an actor stars in a movie all by themselves with no other movies with any other co-stars. So it won't come up. So for this game example, we want this AI character to be hunting down the player. What we're going to do, how we do that is build a graph. So I have a graph representing every valid move between 2 tiles. The starting node is going to be the node where the tile where the AI character is, and the destination is the tile where the player is. This one right here is the one they're closest to. And then run breadth first search, starting at the start node, and then find the player node, work backwards to find that shortest path, and then traverse that path. Maybe I will get back to this homework. It's at least more interesting than degrees of separation, in my opinion. You know, some people will disagree with that. At least the degrees of separation has a real world thing. It's more of a real life thing instead of video game stuff. But I don't know. But this is how we do it. So when you're playing this game, this is what you see. This is how you're going to play the game. You see the actual visuals, the graphics, and everything. But the AI character is only going to see the graph. The AI character doesn't care about the visual representations of all this information. It wants the data structure. It's going to see this graph. Sees this is the starting node. This is the ending node. It's going to run breadth first search, explore all the nodes, and then work backwards from the node containing the player, and go back asking each node, which node found you, which node found you, which node found you, until it gets back to itself. And then it knows that's the path it has to traverse to be able to attack the player successfully. Then we could add diagonals in here too. I don't have diagonals for a very specific reason. It was one of the bonus objectives of the homework was to smooth out diagonals, but this is what the AI would see. The AI is seeing something completely different than what we see when we're playing the game. We have degrees of separation. So how do we do degrees of separation? Well, we have movies. We have movie data in the format that we've been seeing all semester. And for each movie, we want to build a graph. We want to build a graph for the movie. So when we when we process each movie, we're going to take each pair of actors and create an edge between those actors. So when we process the Hunger Games, we're going to create edges between Jennifer Lawrence and Josh Hutcherson, and an edge between Jennifer Lawrence and Elizabeth Banks, and an edge between Josh Hutcherson, I can't say his name, and Elizabeth Banks. So we would have these three nodes all with edges to each other. So we got this little triangle of three actors all connected to each other by edges. And then for the next movie, we're going to add edges between these actors. We can see Elizabeth Banks is the one that's going to connect these two movies together. So we have another triangle here, and then Elizabeth Banks is going to be the glue between these two movies. And then another movie, Chris Pratt and Zoe Saldana are going to be connected together, with Chris Pratt being the connecting tissue there. So that's going to be our graph, and then we run breadth first search. Say we want to find the distance between Zoe Saldana and Jennifer Lawrence. Well, Zoe was in Guardians of the Galaxy with Chris Pratt, who was in the Lego Movie with Elizabeth Banks, who was in Hunger Games with Jennifer Lawrence. So that's three movies we had to traverse. So that's 1, 2, 3, distance 3. So their degrees of separation would be 3 for that one. So we create that graph, run breadth first search, find their distance in that graph, which is exactly their degrees of separation for the homework. So build a graph, run breadth first search. You have two actors. It doesn't matter which one's the starting node and which one's the ending node. Just choose one of them for the starting node of your breadth first search. Run the algorithm. Go into your resulting distance hash map and pull the other actor from that. Whatever value you get, that's your return value. If that actor is not in that hash map, return -1. If either actor isn't in your graph at all, return -1. So you have your edge cases there. But if both actors are in the graph and they're in the same connected component, return whatever that hash map says for the distance of the other node that you didn't use as the starting node. Okay, and I mean, we made it to the end here. I said it a few times. Nobody said anything yet. It's decision time. What do y'all want to see? We can do the memory diagram that I don't think will be super useful. But I mean, we can do it if there's demand. I can take questions on really anything. Or we can just shut it down and end the last lecture early. What do y'all want to see? Because we have time, can we see the memory diagram? Sure. I have 1 vote for memory diagram. Let's do it. And everyone else abstains. Okay, yeah. Nobody else wants to say anything? Yeah, let's do the memory diagram. Okay, so we're going to start with the main method. And this is going to use add edge, not add bi-directional edge. So it's going to look a little different than what you'll do on your homework. So I just want to make sure that's 100% clear. It's going to look a little bit different because of that. So we're going to create a new graph object. We get the constructor, returns a reference to the object that was created. The graph has an adjacency list. We created a new adjacency list in the constructor as a hash map. Get that on the heap as well, but we don't trace the hash map constructor because it's internal to Java. We get to our first add edge call. I don't have much to say about a constructor. We've seen constructors all semester. Add edge, I do have a bunch to say. It's going to take a while to add these edges, and we're going to check if two different paths are valid in this graph. So notice this will be directed edges. We're going to call add edge and not add bidirectional edge. So we're only adding the edge in one direction in our adjacency list. So we're going to call add edge Buffalo to Washington, D.C. So we call add edge. This is a reference to the calling object, which is graph. We're going to call this .add node, which is called through this, which is still the graph OX350. So add node of A, which got the value Buffalo from, which got the value Buffalo as a string literal in the main stack frame. So we're going to check if this .adjacency list contains key of A, that's going to be false. The adjacency list doesn't have any keys. Well, before that was executed, it doesn't have any keys, so that's going to be false. We hit it with the negation, so it's going to be true, so we do execute what's inside the code block here. This .adjacency list .put, so this .adjacency list .put into this hash map here, we're going to put A, which is Buffalo, and new array list. So we're going to create a new array list, and that's going to be the array list for Buffalo. We're going to do the same thing. So that stack frame returns. We get to the next call to add node, Washington, D.C. We're going to do the same thing. Washington, D.C. is not in the hash map. So we're going to initialize the hash map. This is our lazy initialization. This .adjacency list .put, Washington, D.C., new array list. So we're initializing our hash map. If we've never seen this node before, we're going to give it a new array list. And then we're ready to add the edge to the adjacency list as a directional edge, so only in one direction. We have from and to, not just bidirectional, here are two nodes, let's add them. So this .adjacency list .get from, and you should be getting very comfortable reading lines like this by now. I sure hope, at least. This .adjacency list is going to resolve to this reference here, OX200. .get, so we're calling the get, .get, so we're calling get on this object right here. We're calling the get method. And from, every time we have a new expression that we're resolving, we go back to the stack frame. So from is going to be from the stack frame. So even if there was an instance variable called from over here, we're not over here at that point. When we evaluate this expression, the from expression to, these are two separate expressions that we're resolving. So from is Buffalo. So we're calling .get of Buffalo of this hash map, which is going to be OX480. So this entire thing right here is going to resolve to OX480. That's what this expression resolved to, OX480. So we have OX480.add. So OX480 dot, we head over to the object. Dot means follow the reference to its object. At this object, we're going to call the add method. And then to, we have to resolve a new expression, to, so we start over at the stack frame, to Washington, D.C., so we're going to add to this array list the value Washington, D.C., or WDC for the airport code. And these are flights, if the application isn't clear. These are flights using airport codes, Buffalo, New York, Washington, D.C., Toronto. And we're going to say the flights are one way. Now let's do it again. Add edge Washington, D.C. to JFK. So we're going to add node from Washington, D.C. We're going to check this dot adjacency list dot contains key. This dot adjacency list dot contains key Washington, D.C. It does contain the key, so that's true. And we're going to negate it, so it's going to be false, so we do not evaluate what's inside the code block here. And this is how we're doing our lazy initialization. We initialize exactly once for each node. We're going to skip the initialization because we already initialized it. So we don't do anything. Add node of 2, add node of JFK we did not see, so we expect that to be initialized. So we're going to initialize that to a new array list. And then this add node should be crossed out here. This dot adjacency list dot get from, which is Washington, D.C., so that's OX120. So OX120 dot add to, which is JFK. We add JFK to this array list here. And that's that edge. Then we do it again. Toronto, Buffalo. Toronto needs to be initialized. And then we add the edge from Toronto to Buffalo. So this is our final adjacency list. We have an adjacency list. For each node, we have an array list, which are all of the nodes that you can reach from that node via an edge. And since it's not bidirectional, the array lists look kind of sparse. We got 3 edges, so each one only shows up once instead of each one showing up twice like we would expect for a bidirectional graph. So Buffalo to Washington, D.C., Washington, D.C. to JFK, JFK to nowhere, you're stuck there if you go there, Toronto to Buffalo. Those are 3 edges in our adjacency list. We're going to create our first path. This is all internal to Java. The asList call, the ArrayList constructor, all that's internal to Java, so nothing to trace here. We just need to know what the final ArrayList is going to be. Buffalo, Washington, D.C., JFK. And we want to check if this is a valid path. So we're going to call valid path. And we're going to have an interesting situation with the loops. I think we saw this once. We at least saw it with linked lists, which was a little more complex than what we're about to do here. But where we want to iterate over an array list, but we want to iterate over 2 nodes, 2 values simultaneously. So we want to consider pairs of nodes as we're going through this path. So we have to be careful about how we do that, or else we're going to end up with an index out of bounds error. We want to make sure that we check every single consecutive pair of nodes, but that we never go out of bounds and check an index that's not a valid index in this array list. So we have to be careful exactly how we do that. So the way I'm going to do this is initializing I to 0 and then going until I is strictly less than the size of the path minus 1. Now if we're just trying to go through the indices of the path, this is going to get us an index out of bounds error. This isn't going to go over all the nodes. This is going to go through all the nodes except the last one. So usually we would want to go I from 0 to the size minus 1. And typically, stylistically, what I prefer anyway, and what I think most devs do, is I equals 0 to I less than the size. So when I is equal to the size, the loop breaks. So we never check that when I is equal to the size, because that would be an index out of bounds. There's no index at the size because it's 0 to size minus 1. So we do less than, strictly less than the size is going to stop before we go out of bounds. But then, or we could also do I equals 0 to I less than or equal to the path.size minus 1, which might be a little more clear what's happening. We're going from 0 to size minus 1, so we have our 2 endpoints specified very clearly. But here I'm doing both. I equals 0 to I strictly less than size minus 1, which means I is going to go from 0 to size minus 2. Which is what I want in this specific case because I'm going to access the value at I plus 1. So I want to go to I size minus 2. So plus 1 is size minus 1, which is my final value in the array list. So just being a little careful of how I set things up to make sure I'm iterating over exactly what I want to iterate over without going out of bounds. So I equals 0, and I'm going to check, are these two nodes connected? At this point, I is 0, so 0 and 1, the values at these two indices. Path.get 0 and 1, Buffalo and Washington, D.C. Are these two connected? So call the areConnected method, where this is the graph. And I'm going to check if this dot adjacency list dot contains key. This dot adjacency list dot contains key from Buffalo. That's going to be true. I'm going to and this dot adjacency list dot get from dot contains 2. So this dot adjacency list dot get from, so that results to OX480 dot contains 2, which is Washington, D.C. That's true. It does contain it. So this whole thing returns true. And there's a bit of a trick here. I'm taking advantage of short circuit evaluation here. This is something that came up a few times throughout the semester, just as side notes. But I'm really taking advantage of it here, where if the first value of a Boolean AND is false, the second one is not executed. If I have false and anything else, the whole expression is always false, no matter what the second operand is. So Java will short circuit this. It won't evaluate the second operand and just return false. So if the adjacency list does not contain from, and I try to get from, I'm going to get a key error right here. I'm going to get this key does not exist. It's going to throw an exception, which I'm not catching, so my program's going to crash if this is ever evaluated on the adjacency list that does not contain this node. So I can't execute this line. I'll get an error if this is executed without a valid from that's in the hash map, but I know it will exist because I'm checking it right here. I'm checking if it contains the key. So the only way the second operand is ever going to be executed is if the first one is true. And if the first one is true, I know that I do contain the key that I'm getting. So now I can safely get that array list for this key because I know it has to exist, or else I would have got short-circuited. So a little bit of a trick here. Being the last memory diagram, I wanted to throw something kind of fancy in there. That where we have the check, where usually you would say, without short circuit evaluation, you would say if this dot adjacency list dot contains key from, then return this dot adjacency list dot get from dot contains 2, else return false. You would do something like that and do the same thing, but in a few extra lines of code. If you get comfortable reading short circuit evaluations, this is a much cleaner way of representing it. Okay, so that returned true. So we're going to increment I. I is now 1. And now we're checking get I and I plus 1. So path.get I and I plus 1, Washington, D.C. and JFK. We're going to check if this dot adjacency list dot contains key Washington, D.C. It does. Then get it dot contains JFK. It does. So this is going to return true. And now I is going to go to 2. Oh, I should add all the details of my memory diagram here. I should cross out 1. I is going to be 2. So 2 less than path.size minus 1. So 2 less than path.size, which is 3, minus 1 is 2. So 2 less than 2 is false. So we're going to break out of the loop. And we checked exactly our 2 pairs of nodes that we wanted to check. So we did check everything that we wanted to check and stopped before we went out of bounds. Because if I is 2, I plus 1 is 3, there is no index 3, and we'd get index out of bounds error. So we did exactly what we wanted to do there. We were careful with our endpoints of our array list and got everything we wanted out of that. That's one thing. If you have a bug in there, that's one where the debugger would really show. Stepping through your loop in the debugger, you would see if you either missed a pair of nodes or if you went out of bounds, you'd obviously get an error and you'd know about that. But you could see exactly why you went out of bounds with the debugger. and we get to return true. So if this is ever true, we're going to return false. So if we made it through this whole loop and never returned false, that means each pair of nodes are connected, so we can safely return true out here. At a glance, it might look like this method just always returns true, but once we look and see this return false, well, if this returns true, if we ever get here, we never did return false, so we must be good. So we print true to the screen. Create another potential path, this time JFK, Washington, D.C., Buffalo. Check if it's a valid path, and do the same thing. I equals 0, we're going to get JFK and Washington, D.C. So JFK does not contain Washington, D.C. So we're going to return false. Our connected returned false. We negated it to true. So we went into the code block, returned false. We're never going to get to this return true because we're returning false. That just shuts everything down. The whole stack frame is done. We return false, and then we print out false in the main stack frame. That memory diagram actually doesn't take that long to go through. So I guess I'm back to taking suggestions. I thought that memory diagram took up like a full lecture. I must be thinking of something else. So, any other requests? Because I think I got everything I need to say to prepare you for Task 8. You're well prepared for Task 8 after today's lecture. If you disagree, I want your questions. If you agree, let's take this time to work on the homework. I guess it is 40 of you have finished Task 7. That ain't so bad. I'd like the number to be higher, but, you know, I'll take what I can get. What concerns me is that out of the students who have not completed Task 7, only 4 of them have submitted anything, which I guess is good and bad. I mean, everyone who's attempting the homework, most students who are attempting the homework have been able to complete it, which is good. What concerns me is that 39 students have not attempted the homework. And that's out of the students who have not resigned. So that's a little bit of a concerning stat. So I'm happy that, you know, all y'all got to do is just do the homeworks. Not gonna apply to anyone who can hear me, so not worth ranting about. But just so you can share my pain, is I just got to get students to do this stuff. Like I feel like I'm preparing y'all well. If anyone who's attempting the homework is able to complete it, how do I force students to just do the damn thing? Off-topic question. If we pass the objectives on the midterm, the pass part incomplete, and there's no further opportunity to get objective points on the final. Yeah, if you have both learning objectives on the midterm, there's no reason for you to take the final. You shouldn't take the final. This is the last thing, aside from finishing up the 8 tasks, this is the last thing you should be doing is watching this lecture. There's nothing for you next week. Office hours if you want help finishing the tasks, and that's it. No final. I won't even send you an email for the final, by the way. I'll send one. I should send one Monday, actually. I'll send like the here's what to expect for the final email. And for everyone who shouldn't be taking the final exam, I'll send a confirmation and say, hey, just reminding you, you don't need the final exam. On Tuesday, I'm not going to send you an email. I'm not even going to send you the links for the final because you don't need it. But anyone who's taken the final, I'll send them the, here's what to expect. It's just like the midterm. Good luck. If we aren't taking the final, do we need to do anything to indicate that, or do we just not come? Yeah, just don't come. You're done. Yeah, and this is 100% of the content. I'm done. All lectures are out there. Everything's in your hands now. If you're done with the final, most of you don't have to take the final. There's not many students who even have to take the final at all. The kind of sad part about it is there's a strong correlation between students who are missing final deadlines and students who failed the midterm also. So a lot of the students who didn't pass the midterm, who didn't get their learning objectives on the midterm, also failed on missing final deadlines. So very few students fall in that category who are keeping up on the tasks but couldn't get the midterm. Very few students in that category. Not none. It's still a decent portion of the class, but not a significant portion of the class. But yeah, you just don't come. I'm expecting. How many students am I expecting for that? I can give aggregate numbers, right? Let's sort here. Sort here. And I'm losing. The number was higher, but it keeps going down. Every final deadline that goes by, I expect fewer and fewer. There's less and less. Yeah, only 15 students are taking the final as of right now. Which at least makes sense. Like if you're falling behind on tasks, you don't have enough time to study for the midterm. And what I suspect more out of a lot of the students who have failed already is they probably just didn't give the course overall the attention that it needs, that it requires. Which sucks. Like, again, what do I do about that? Like, I don't think there's anything I can do from my point of view. Like, do I go to their home addresses and knock on their door, kick them a few times, and be like, do your shit? Like, there's nothing I can do at that point. I can build incentives into the grading structure, but at a certain point, like, some students just don't care about their grades enough to do anything, and there's nothing I can do there. All right, any other questions? I don't want to end lecture on a downer like that. Do we have a more positive end? Yes, you don't have to take the final. That's more positive. I can just answer the question again. But I do. I mean, I want to see students pass and succeed. That's my issue I have with it. Once there's nothing left for me to do, I just kind of have to sit and watch them fail, and I don't like that. Have I not refreshed this page, by the way? It's still saying week 1 is the current week. I don't think I ever refreshed this page. Jump to current week graphs. With the whole semester without refreshing. I guess we can go through the... Since we do have a little time, just a reminder of what to expect. You all know about your 8 for the quizzes. Those are posted on Autolab. For the expected deadlines and the late deadlines, I'll compute these as soon as I shouldn't say as soon as, just in case I don't do it right away. But when the Task 8 late deadline passes... So the Task 8 deadline, Tuesday morning, that's when all of the I have all the data I need to process all of the application objectives. So I'll process them after that deadline. So that's probably what I'll do during the final exam, actually, since I'll just be here, sitting here watching Piazza and hoping things don't fall apart again. I'll be processing the application objectives for the tasks and post them to Autolab. So I'll have a new thing on Autolab just to give you confirmation. Like you should know what those numbers are going to be, but just to give you confirmation, and especially if I do make a mistake, I want you to have a chance to double check my work and let me know if I did make a mistake anywhere in any of your tasks. There's some little things that sometimes come up. I know to check for them, but just in case I miss them, like when a student submits, gets credit, and then submits again later, like after the next deadline, and gets credit again, I do look for the first one. I make sure I double check that. But if I miss some edge case like that, I want you to have a chance to say, hey, don't post this grade to the hub yet because it's off. I got more application objectives than that. But that's what to expect there. So on Tuesday, you'll be able to confirm all of your application objectives. And then once the task 8 final deadline, which is not for a while, it's about a week and a half from now. Well, it's 11 days from now because that's when the final deadlines are. 11 days from now, that's when I can post final grades to the hub. Unless everybody finishes task 8 before then. Yeah, but this is when you should expect. So Tuesday, July 9th, that's when you should expect final grades posted to the hub. So that's the timeline of everything else. And yeah, I ran out of stuff to ramble about. So if there are no questions, I think we can just shut this down early and start enjoying the rest of our summers. Yeah, take care, everyone. Enjoy your summer. That's it for me. I got no more lectures for you. 10 out of 10, 100%. 10 out of 10 lectures. 100% of the content's covered. If you haven't completed the tasks are all in your hands. If you have to take the final, good luck on the final. Good luck with everything. Might see you in 312. Yeah, I hope to see you there. Course was kind of fun. Thanks, Tro. Happy to hear it. All right, have a great summer, everybody. Take care.